Microcornucopia, issue number 46, March 1989. Page 8, and the title of the article is The Art of Disassembly. Subtitle, Getting to the Source of the Problem when the Object's the Data. We're going to skip to the section titled How a Disassembler Works. There are two types of disassembler programs. The first assumes that every byte or word it reads is an instruction. This works until the disassembler reaches the first data area. The unassemble command in debug is a good example of this kind of disassembler. The main disadvantage to this method is that it requires a great deal of highly skilled operator intervention. More sophisticated disassemblers also assume the binary code is all instructions, but they can later correct themselves and determine which addresses are data and which are instructions. But even these disassemblers will sometimes need help. Sorcerer falls into this category, and the intervention it requires is discussed in detail later. The second type of disassembler makes no initial assumption about data or instructions. In this case, the operator must tell the disassembler the entry point into the target program. The disassembler then starts translating instructions from that point until it encounters an unconditional jump or a subroutine return. It then stops translating and stores the beginning and ending addresses that define this portion of the program as instructions. As the disassembler translates, it notes the destination addresses of all conditional jumps and subroutine calls that it encounters. It stores these addresses in a table and uses them as new entry points into the program, since it can be sure that these addresses are for instructions. The disassembler goes back and forth through the code until it has used up all the destination addresses. Thus, it generates a map of the instructions. It assumes everything else is data. What the disassembler calls instructions are usually instructions. However, the rest isn't always data. Instructions will be missed if they aren't called by the rest of the program. There are two primary causes for uncalled code. 1. Multiple external entry points to the program, or 2. Non-accessible code produced by compilers. The non-accessible code is not important since it is never executed. However, multiple entry points should be caught by the operator. The listing produced by the disassembler should be a standard assembler format. If not, you'll have more difficulty reassembling the program after modifications. A good disassembler will even add the assembler directives. The disassembler has no knowledge of what the program does or how it does it. The listing will be labeled for the explicitly called data and instruction locations, but they will have some sequential format such as lock_12 or data_24. These names are used instead of more intelligible ones such as get RS-232 input or screen offset. One of your major tasks is to work through the code, figuring out what's happening, and change the sequential labels to meaningful ones. This process is complicated if the disassembler mistakes data for instructions or vice versa. Most of the commercial disassemblers advertise a feature called commented code, where the disassembler automatically puts comments in the listing. This is not really as useful as it seems. Remember, the disassembler does not understand the target program, so its comments can only tell you a bit about what is happening, not why. For example, Sorcerer will comment a LODSB instruction with what you see in red here. This helps if you're inexperienced in 8086 programming. But what you really want to know is the purpose of the instruction. In this case, it might be get byte from file name for parsing. Now that we have seen what a disassembler does and doesn't do, let's look at the overall disassembly process. The basic steps are 1. Examine the machine code using debug. 2. Feed the machine code to the disassembler. 3. Examine the disassembler's output. 4. Determine new settings for the disassembler. 5. Go to step 2 until the listing is satisfactory. Steps 2 and 5 are self-explanatory, and step 4 is disassembler specific, so we'll concentrate on steps 1 and 3. So in step 1, you use debug to dump the target code. This is to give you a general idea which addresses contain data, look for ASCII strings, and initialize data areas. ASCII strings are readily recognizable from the dump listing. Record their beginning and ending addresses so that you can tell the disassembler that this is a data area. It will appreciate all the help you give it. By looking closely at the strings, you will be able to glean additional information. If the strings end with a 0, they are in the ASCII Z form. This means the program was probably compiled with a high-level language. For instance, C uses these strings. If the strings end with a $sign, then the source was probably an assembly program. You will be able to recognize the initialized areas if you get large areas of the same byte. In particular, an area initialized to 0 is easy to notice. If you're not sure, use debug to unassemble the code. If you get the same instruction 100 times, then it's probably data. 2 in a row, well, they could be data or instructions. When in doubt, assume instructions. Now for step 3, examining the disassembler's output is the hardest part of disassembly. This is a job for an experienced assembly programmer. The key to successfully disassembling the target program is to examine the listing instruction by instruction to decipher the original program logic. You must understand the target program so that you can add labels and comments. Start at the beginning and follow the program flow. When you come to a conditional jump, try to figure out why the jump exists. Record the conditions and take both branches. You may not initially know why the jump is there, but by comparing the instructions following both branches, you can figure it out. When you get to a subroutine call, note the contents of the registers. Then go to the subroutine code. Try to determine the purpose of the subroutine. Record which registers it uses for input and which it uses to return values. Don't try to get everything straight. Get as much as you feel you can, then rerun the disassembler with the new information. You'll be surprised at how much easier the second examination will be since the new listing will have some descriptive labels. Instead of trying to remember that sub 23 reads a sector and then sub 15 writes a sector, you'll have changed the labels to read sector. Oh, and write sector. If you can make the disassembler put comments in its listings, do so. You want as much information as possible on the listing. As you examine the listing, be sure that the data is really data and that the instructions are really instructions. These 3 goals, deciphering program logic, adding comments and mnemonic labels, and ensuring accurate translation, have a synergistic effect. As you improve one, it's easier to improve the others. Conversely, you cannot complete one until the others are nearly complete. Working on these 3 simultaneously is the secret to disassembly. Now that you have thoroughly examined general disassembly, let's look at Sorcerer. In the rest of this article, I'll explain how Sorcerer works, how to use it, and some things about it not mentioned in the operator's manual. If you haven't read Sorcerer's user manual, the last section may be hard to follow. So Sorcerer is a multi-pass disassembler, where you set the number of passes from 2 to 5. On the first pass, Sorcerer assumes all the code in the target program is made up of instructions. As it goes through the code, it stores a symbol address for use in the next pass. It maintains 3 symbol tables, 1 each for data, locations, and subroutines. On the next pass, it looks at the symbol tables and makes sure the item referenced is valid. With each additional pass, Sorcerer refines the symbol tables and its ability to distinguish instructions from data. The number of entries in each table may decrease as invalid entries are recognized and removed. On the last pass, it writes the listing to disk. Sorcerer works through the program sequentially. It does not take any jumps or subroutine calls, and as it works through the code, it maintains a set of simulation registers which it tries to keep updated. These registers are used in producing comments or finding the address of jump tables. Since Sorcerer does not jump or loop, the simulation register will be incorrect if the program changes a register and then jumps to a previous location. You control Sorcerer via a command menu or a definition file. The definition file has 3 sections. The first is for control information and duplicates all of the commands available from the menu. Section 2 is for range definition, and it specifies how Sorcerer processes a range of bytes. The third section is for reference definition. It specifies how a particular address is to be treated. Figure 3 has sample definition files. The range definition tells Sorcerer which portion of the target program are data, which are instructions, which are unknown, and which are ROM. So Sorcerer will read these directions and it will skip the data areas during the first pass. This prevents bogus labels from being entered into the symbol tables. Reference definition allows finer control. You specify individual addresses and direct how Sorcerer is to treat those addresses. For data, you can specify a byte, word, D-word, ASCII, or even a structure. If you tell Sorcerer that the data item is an offset, it will add the offset directive and target label. Sometimes Sorcerer will override your range definitions. This can happen if you miss a data area and Sorcerer erroneously translates the data as a jump to the area you defined as data. Sorcerer will then believe the bogus jump and label the area you previously defined as data as instructions. Some of the definition file control commands are sequence sensitive. For instance, the header command must be after the input file name command, or you'll get the default header. The keep segments command must be before the input file name command. Sorcerer will accept almost any string as a label, but it's a good bet your assembler won't. If you plan on reassembling the code, save yourself some pain later and use only labels acceptable to your assembler. If the target program contains an int 20h, Sorcerer does not recognize this as the end of the procedure and does not put the required end p directive into the listing. Sorcerer has a number of built-in labels which it uses when it feels the need. They include a label for copyright statement, a start for the program's entry point. There's an int xxh ext for external interrupt entries, and strategy and interrupt for device drivers. You have no control over these labels. If you use the repeat option to define a data area and you miscount the number to be repeated, Sorcerer will add bogus bytes as needed. This can rear its ugly head if you have defined ASCII text and it contains a copyright. The built-in copyright label will be applied and your repeat count will be wrong. When you define segments via the range definition section, you must explicitly specify the last byte's address. There is no end of code operator. The best way to find the address of the last byte is to load the program with Sorcerer, then note the last address as shown on the main menu. The addresses in the range definition section should be contiguous. If there is a gap, Sorcerer will skip the gapped code and generate an ORG statement. This ensures the subsequent addresses are in their proper place, but the gapped code is removed. If 2 range definitions overlap, Sorcerer will process the overlapped code twice. If the first range is a data definition and the second is code definition, Sorcerer will output both the data and the code. Figure 5 illustrates this. The keep segments command is not explained well. It tells Sorcerer which of 2 sets of range definition to use. The first is internal to Sorcerer and is created as Sorcerer processes the binary code. The second is the one you write in the definition file and is optional. The keep segments command tells Sorcerer to use either its internal definition file, the one from the definition file, def, or to use both. If you haven't written a range definition, use the default file option. If you have a written range definition that includes the target program's address, use the def option. If your range definition contains only addresses outside the program's area, such as the BIOS data area, use the both option. Sorcerer will process the code twice if your range definition covers the program's addresses space and specify both. Labels can be added to the disassembler listing at will. However, you should restrict their use so that they are present only when they are the target of an instruction. For instance, if you add extraneous labels to instructions, it will be unclear which labels are decorations and which are the destinations of jumps and calls. Unfortunately, Sorcerer requires you to specify a label in order to add a comment. I recommend you use a sequential label notation so that each label is unique and is distinguished from functional labels. If Sorcerer's analyzer makes a mistake and translates data as instructions, these bogus instructions can cause trouble further down the line. Any addresses the bogus instructions reference as data will be marked as data, even if they are really instructions. Bogus jumps or calls will mark the destinations as instructions, and these second-generation bogus instructions can cause additional trouble. If you find the sorcerer has made a mistake, don't just fix the part you found. Backtrack until you find the root cause. The cause will always be the bogus instructions. The more passes you specify, the better the analyzer can separate the data from instructions. 5 passes will produce the best solution, and you can use the cross-reference option by using cross-reference. You can backtrack to the source error. Sometimes a label will not have a cross-reference. This indicates the label was created by a bogus instruction that the analyzer has converted back to data. You can add the cause by reducing the number of passes and then using the range definition to fix the problem. Okay, so if you hung with me through all of that, that's the end of this article. I could pretty much summarize it by saying the first part really puts your mind in the right place to understand what disassembly even means, and the second part is a very specific type of disassembler called sorcerer. Thanks for watching.